Hello, this is Miss Moore, and today during chemistry we're going to discuss diprotic and polyprotic acids. Today's essential question: how does the use of polyprotic acids change acid-base constant calculations? And big hint here, calculations. Make sure you have your calculators handy. Okay, let's start with a definition and overview of polyprotic acids. So, definition. A polyprotic acid is an acid that contains two, which would be diprotic, or more, which would be polyprotic. So let's try that again. A polyprotic acid is an acid that contains two or more ionizable protons, which are hydrogen ions. So what did I just say? Let's look at an example. It'll make a lot more sense. So sulfurous acid, or H2SO3, has, right here, two H's that can be ionized or released in water. And phosphoric acid, H3PO4, has three hydrogen ions that are ionizable or can be released in water. So we have here a diprotic acid and polyprotic acid. All right, so there are the definitions. Let's talk about some behavior of polyprotic acids. Polyprotic acids ionize in a stepwise fashion, with each step having its own ionization constant, or Ka value. So that means that they ionize or break apart step by step by step. So, example, we have here H2SO4 mixed with water gives us H3O and HSO4. So you can see that one of the two hydrogens was ionized. And this first step has a Ka value of 1.6 times 10 to the negative 2. From there, we have HSO4, note HSO4. Okay, so HSO4 with water produces more H3O and now SO4 2 minus. So the second hydrogen has now ionized. And take note of the new Ka value. It is now 6.4 times 10 to the negative 8. So let's look at those Ka values one more time. The first ionization constant is 1.6 times 10 to the negative 2. Just because sometimes it's hard to visualize scientific notation, that means it's 0.016. The second Ka constant is 6.4 times 10 to the negative 8th, meaning 0.123456764. You note a pattern here? The first ionization constant is way, way bigger than the second ionization constant because it gets much more difficult to remove successive hydrogens. And that's because after the first hydrogen's removed, the acid now has a negative charge, making it more difficult to remove a positive charge, another positive charge from it, giving it an even larger negative charge. Okay, let's just try this out real quick. Let's write the equilibrium expression in Ka values, or expression for the ionization of the diprotic acid H2CrO4. All right, so to do that, we're going to start with H2CrO4, and this is going to be aqueous plus water, liquid. Producing, we're going to ionize only one of the hydrogens. So our products are going to be HCrO4 minus aqueous plus H3O. So let's go ahead and do the second step. We're going to be taking that conjugate base is now going to be our acid. So we're going to have nope, I almost put a 2 there. HCrO4 aqueous. And this is still in the water because keep in mind, we're not picking these things out of the water. Okay, as this is going on, this, and this is all still in the same environment. Okay, so where are we here? Producing, we're now going to ionize our second hydrogen. So we're going to end up with oops, wait, let's go back to here. Forgot to put a minus. I hope you were shouting that out as I missed that. CrO4 2 minus. Oh, what a mess. 2 minus aqueous plus more H3O. Okay, and there is the step for ionizing this acid H2CrO4. So now let's write the ionization constant equations. So for step 1, we'll have Ka1 for step 1. We're still going to have the products over the reactants, so we're going to have concentration of HCrO4 minus H3O over concentration of H2CrO4. And remember, we don't involve water because it's not in an aqueous state. Okay, and then for our Ka2 for equation 2, we will have the concentration of CrO4 2 minus H3O over concentration of CrO4 2 minus. So there you go. That's how you write the equilibrium expression and ionization constant expression or equations for a polyprotic acid. All right, let's try some calculations here. The good news is it's really not any different than these same sorts of calculations with monoprotic acids. The bad news is it's often more than one step. All right, so we're going to do this with a practice problem. So practice problem, calculate the pH of a 0.1 molar solution of H2C6H6O6 solution and the equilibrium concentrations of all the species involved. And we have our Ka1 and our Ka2. I guess the first thing we should do is write our equilibrium expression. So we know we're going to start with the acid H2, C6, H6, O6, aqueous, plus water, which is liquid, producing, we're going to lose 1 hydrogen, giving us HC6H6O6 minus aqueous plus H3O. And unfortunately, that's only step 1. So for step 2, we're going to start with that guy there. And we will have HC6H6O6 minus aqueous in water producing C6H6O6, 2 negative aqueous, and forgot my plus sign, plus H3O. Okay, so there is our step 1 and 2 equilibrium expressions. We can only do our calculations one equilibrium expression at a time. And being that I have limited space, I'm going to get rid of the second expression for now. And let's write out our rice box. So rice, we've got our reaction. So H2C6, H6O6, and we can skip the water. C6, H6O6 negative, and H3O. Our initial concentration is 0.100, and then 0 and 0. We don't have enough information to know the change, so we're going to have minus some change and plus some change. So that's our C, and then at equilibrium, we will have 0.100 minus X, 0 plus X, or just X, and 0 plus X, or just X. Okay, I moved our rice box to a new page, so I have a little bit more room to work. So remember that Ka, in this case Ka1, equals the concentration of our products over our reactant. Okay, and so that will give us, let's see, what was our Ka1 again? 8.0 times 10 to the negative 5th. So we'll have 8.0 times 10 to the negative 5th equals X and X, right? So X squared over 0.100 minus X. And remember, this is a weak acid, so we're going to assume that the X here is extremely small. So we're going to ignore it, although we do need to check to see if we're right later. All right, so then let's get rid of the 0.1 by multiplying, not by erasing, by multiplying it on this side, giving us 8.0 times 10 to the negative 6th equals X squared. So to solve for X, we will square root both sides, giving us 2.8 times 10 to the negative 3rd. And that's what we got for X. So remember to check to make sure that our X was really small. We need to take that number and divide it by our original concentration. And as long as that result ends up being less than 5%, we're good to go. And it looks like it is about 2.5%. So our assumption that the X was small enough to ignore was appropriate. All right, so we now have some concentration information. Let me get rid of these X's here, give us a little bit more space. All right. So we know that our hydronium ion concentration is 2.8 times 10 to the negative third, as is our conjugate base, or HC6H6O6, 2.8 times 10 to the negative third. And I guess I should not have deleted this last box because it was 0.100 minus X, right? So that gives us a concentration of our original acid of 0.097. Okay, guess what? Step 1 done. However, we're not. We've got to move on to step 2. Okay, on to the second step of our ionization. So we've got to do the whole rice box all over again. So starting with our reaction, we have HC6H6O6, and we have C6H6O6, and we have H3O. So there's our initial reaction, or a reaction. Now for the initial concentrations, it's a little bit different this time. We don't get the initial concentration from the beginning of the problem. We get the concentration, because this here is what we're looking for, right? And that is our concentration. The equilibrium concentration we just calculated, 2.8 times 10 to the third. And negative third. And there's another difference. We actually have a starting concentration of our hydronium ion. Again, 2.8 times 10 to the third. Because this is all happening at the same time in the same reaction dish. So 2.8 times 10 to the negative third. What we do not have anything of is that guy there. All right. So now our change, just like last time, we don't know how much it's going to change exactly, but this one will decrease by some X, allowing these guys to increase by the same X, which means our equilibrium will be 2.8 times 10 to the negative third minus X, 0 plus X, or 0, or X, and 2.8 times 10 to the negative third plus X. All right, so next up is to calculate our Ka2 this time. And our Ka2, I got to go back and check, right here, 1.6 times 10 to the negative 12. And then that's going to equal the product of these two, right? So we're going to have, X times 2.8 times 10 to the negative third plus X over this one here, which will be 2.8 times 10 to the negative third minus X. This is starting to look complicated, but here's the good news. We're going to assume again that these two x's are so small that when we add or subtract them, it's not going to make a difference, although we'll check. So we get to get rid of these. So then this turns out to be really easy. We divide, and now look, our x equals our Ka2. So x equals 1.6 times 10 to the negative 12th. And again, to test our assumption, we should, of a small x, we need to divide 1.6 times 10 to the negative 12th by our original for this part of the problem, concentration. And that will definitely give us less than 5%, so we're good to go. All right, everybody good so far? So next, let's calculate all these concentrations. Let me get rid of a few things here to make it so there's some room to write. So now let's plug x into each of these equilibrium concentrations to figure out our concentrations. So 2.8 times 10 to the negative third minus 1.6 times 10 to the negative 12 gives us, drum roll please, 2.8 times 10 to the negative third. And what about for the next one? Well, that's easy, 1.6 times 10 to the negative 12th. And how about our H3O? 2.8 times 10 to the negative third. Oh my gosh. Let's go back and check something. Well, wait, let's not go there yet. So we now know the concentrations of all the species from the first step and the second step. We now need to calculate H3O. Well, H3O at the final step was 2.8 times 10 to the third. Did it change? Look at the first step. We still basically have the same concentration of H3O. So guess what? We could have gotten the pH from the first one. And now, before you get mad at me, I want you to know something. That's only true of a weak acid. Okay? We'll get there in just a second. Let's calculate the pH of this solution. Remember that pH equals negative log of the H3O concentration. So when we put that into our calculators, we should end up with something like 2.55. All right, so now you know how to figure out concentrations of all the species of a diprotic acid, and it would be the same for a polyprotic acid. It would just be more steps. And you now know if you only are asked the pH and it's a weak acid, you can stop at the first step because there's so little. Let's go to the next one. There's like no change. Nope, no change in the concentration of H3O. So you only have to calculate H3O, or the pH, from the first step. You will find if it's a strong acid that the H3O concentration will change a lot in the first step, and it'll still change again in the second step. So you're gonna have to go through the multiple steps to calculate the pH. Okay, so folks, hopefully you see that besides this being sort of long, it's really no different than what we've been doing with a monoprotic acid, and that's it for today. Have a good one.